What are we thinking? Yeah, what's up?
You go.
Did you go over binding energy and how that works? There's a question on the quiz last week on it.
Yeah, absolutely. And then what else do you want to see? Yeah.
On the homework, it was like the valence electrons, like sometimes it's 4s2 and other times it's like 4s1,
Mhm.
3d10. So I'm just gonna use one like that.
Yeah, absolutely. Alrighty, so just gonna try and move my Zoom so I can see that. Alright, so when we talk about binding energies in the quiz last week, I don't see the quiz, so I don't know the exact question that we're talking about. Do you remember what the question asked?
Oh, not exactly. It's hard.
Okay, so I'm assuming they're talking about like the energy between two atoms. Does anyone else remember the question was?
This is a question on the homework.
Okay. So I'm assuming this has to do with like the energy between two atoms and like the attraction that they feel. If I'm remembering this correctly. If you find the question, let me know in case
Almost there.
yeah, no problem. I don't know, my technology is failing me as well. So what we know, right, in an atom, we always have a nucleus that has protons in it and then the electrons around it. And that kind of cancels it out. But that means that when we have like a sodium ion, right, we have sodium here and we have chlorine here. The nucleus of your sodium atom is going to be attracted to the electrons of the chlorine atom and then vice versa. Additionally, right, you have your positive of your sodium ion, which we just learned about today because it loses that valence electron. And then we have the negative of our chlorine atom, right? We also talked about that today because it takes that electron away from that sodium atom. So now we create this bond between them where we have a sodium bonded to a chlorine or something like that, right? I mean, this can also be for covalent electrons like we saw at the end of class where we're sharing stuff now, right? We can have a carbon attached to a carbon, we can have a carbon attached to a hydrogen bonded like that. So this binding energy has to deal with like the attraction between those two atoms, right? When we're giving electrons to each other, right, we create an ion and an ion and an ionic bond. That's going to increase our binding energy because they're more attracted than if they're covalently bonded.
Okay, because I thought I got this question.
Okay.
So it gave us like a whole bunch of binding energies for different metals,
Mhm.
and then it gave us their wavelength and said photoelectrons were seen, and then from that they were supposed to identify the metal.
Okay. So it's slightly different than what I was thinking. We can definitely do that. So when we talk about binding energy, it's still an energy, right? So anything that I just said now still applies. Right, the energy is going to be different between those two, but that's also like a quantitative value that we can say. So if we have a binding energy, this could be something like 6.34 times 10 to the negative 19 joules. Okay, right, so you're given a whole bunch of binding energies, you're given a whole bunch of these joules. We want to know in our atom if our energy levels, right, this is n equals 4, this is n equals 3, n equals 2, n equals 1. If that binding energy is enough to excite this electron up to like this weight or this energy level. Okay, right, this change here is going to be your change in energy, which would cause, you know, a difference, and there's a certain quantitative gap between the two of them. Okay, so in order to find out what that wavelength would be, right, if we take this binding energy, how would we find the wavelength of that photon that would be emitted from it?
We just use the Planck's constant and all that to get the
Yep, so we have two equations, right? We have energy is equal to h times frequency. We also have c is equal to lambda in frequency, so we can say that energy is equal to hc over lambda. And once we know that, we can use our energy, our two constants to find lambda. So let's find what lambda would be for this energy. Okay, so I got a wavelength, 314 nanometers. Does that make sense how we solve for that? Yeah. Okay, so now your question is saying like, will this be seen? So you kind of have to know what your like visual spectrum would be, right? So if this is in the range of the visual spectrum, then you're going to be able to see it a little bit as a color. Right, if there's a threshold that says like, you know, it will see yellow and it gives you the yellow spectrum for it. If it falls between that yellow spectrum, then it would be seen. Right, does that make sense on how that question's asking? So basically the whole point between this finding energy is saying that we know that the energy gaps between our energy levels is defined, right? We know how big that difference is going to be. So if we need to excite this electron, or if it needs to fall down to emit a photon, right? Because if it falls from n equals 4 to n equals 1, then it emits as a photon. Will this photon have enough energy to reach the visual spectrum, or will it have enough energy to have a color that they are specifying for?
Okay, so then once you find the different wavelengths, it had like 3 different options of having then, and how do you use that information to determine what metal it would be? Because it had like 5 different metals, different kinds of finding energy.
Yep, so then I think you would, are you given any more information on the metals?
No, just their electron binding energy, and then it has the wavelengths and then the photons.
Okay, so if you know, like, if you find all those energies in the corresponding wavelengths, you look at the wavelength for the metal and see if they correspond with each other.
Okay.
Right, so if we said that we had a metal and it had a range of 300 to 350 or something like that, right? Then you would say, okay, you would be able to see this because it falls within that range.
Okay.
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 Does that make sense a little bit more?
Sort of. I'm just confused because like this particular question has it.
Yeah.
Like, thanks. Yeah. It has the like, so here's our metals, and then here's the wavelengths, and I was like, well, this metal is, so how do you use, so I know like that's how you determine them, and then you can see if they're seen or not.
Yep.
And then how would that make that clear?
Okay, so then okay, so we can just solve this, right? So let's say with 430. We wanted to plug in 430 for here instead, so it would be 6.626 times 10 to negative 34. 3.00, and then 4.30 times 10 to the negative. I believe this number should go up. Yeah. What's the? Did you get the? I think my math walls are up there.
It's saying like how it did this was, it was solving for the energy. of the wavelengths. And then, so you found the binding energy, I guess. And then it said like if it was greater or less than the first 2 lasers, then it would be. That would help determine.
Yep, okay, so right, we found that our wavelength would be 462 nanometers. So we're doing it just like backwards in how they said it, right? So what options did they give you for your wavelengths?
We had 532, 488, 308, and 308 was something else.
Yep. Okay, right, so here we say, okay, 308 can be seen, these two cannot be seen, right? So finding the wavelength, we say, okay, 462 is a shorter wavelength than 308. So we know that we can still see, we know that we can see 308, but we can't see 488 because it's falling in between here. Okay, so when you look at if you take all the energies and find the wavelengths, you want to see there's probably gonna be one where it might be,
Oh, where it's in between those.
where it might be in between here, it might be up here, and it might be down here, right? So if it was up here, then you would be able to see 308 and 488.
Okay.
So all the numbers that are greater than whatever we get, we can't see.
Right,
And
yep,
all the ones below, we can.
yep,
Oh,
because if we look at our visual spectrum, look at our visual spectrum. Over here at the long wavelength. This is our radio waves and then infrared. So we know that red is over here in terms of our visual spectrum, and then violet is over here. And then ultraviolet right here, right? So the longer or the shorter the wavelength, the more closer it gets to violet and UV rays. We don't see those, right? We don't see gamma rays or anything. So if it's less than the value you find, you're able to see it.
Okay, so you'd want it to fall between 48 and 308. You want to try and find
Yep,
what is in between what can't be seen, what can.
yep.
Okay.
So your other metals, right? I'm just gonna mix them up, right? It might be like strontium, it might be calcium, it might be magnesium, right? Those might be where those other ones fall. And so we know that, okay, if this was magnesium, I would be able to see all three of them because maybe this wavelength is 255, right? So then if it's 255, then I can see all of those.
Okay.
Or I'm sorry, I wouldn't be able to see all of those.
Wait, why? Sorry.
Right, because if it's 255, we know that, right, we can't see anything above it. The only wavelength we can see is 255 or below it. Right, we saw 462
Oh,
here, right? We can see 462 and everything below it because that's closer to the red side.
Okay.
Okay, if this was 500 here, right? We would be able to see 488 and 308,
So you see that and everything below it?
everything below it. Yep,
Okay. And so since 308 was the only one that could
to be
be seen.
seen. We know that this one at 462 means that we can see 462 and everything below it.
Okay, but like the 5, whatever, you can only see that, but you couldn't see 48 because
Right.
it was not. Okay.
Right.
Thank you so much.
Yep.
That makes so much.
Does that make a little bit more sense for
Yeah.
everyone in that question? It's just having to deal with like wavelength and energy relating those two is what I was looking for. But then it gives you a little bit of a puzzle as well. But if you're able to find wavelength, then like that's going to be the most important part. Any other questions? Sorry, I don't think it's a little confusing. Right, so the whole point of this is that you can see anything less than or equal to the wavelength that you can see. Anything? Cool. Okay. I guess I'll turn this.
There was a question from the quiz 4 that I couldn't figure it out. And it was asking for let's see if I can find it. What volume of hydrogen sulfide is formed from the reaction of 572 milliliters of a 1.76 mole solution of hydrochloric acid with excess Na2S. The reaction is maintained at a pressure of 1330 torr at a temperature of 22 Celsius.
Okay, can definitely go over that. Let's, I'm gonna try something. So and then if it just. Okay. We'll do that question and then we'll do the random selection question. Okay, so I just look at your question. we have Na 2S. Okay, sorry for my horrible handwriting. All right, so this question, right, we're looking for the volume. We're given this reaction. Looking for the volume after we have this milliliters and concentration of HCl, and we have our pressure and torque. So the big thing here is to realize that you have two solutions coming together and you're going to form a gaseous product. Okay. So we're going to be working with our gas laws here after we find how much we're like starting with from our HCl and your excess sodium sulfide. Okay. So if you told you that we're working with gas laws, right? Because we have volume, pressure, and temperature. What else do we need from gas laws in order to use this equation or start off this question? We need our moles, right? How are we going to find our moles?
I used to use the concentration, so 1.76 over 0.572, because you needed to, or I'm sorry, 1.76 equals the moles over 0.572.
Awesome, right? So when we look at this HCl, we know that this is going to be our limiting reagent because we have excess sodium sulfide. So in order to find moles, we're going to use our concentration and our milliliters here. When we solve for molarity, or we use molarity, that's always going to be in moles over liter. And so we need to make sure that we change our milliliters to liters. And so right, like we said, we're going to have 0.572 for our volume here. Right, so in order to find moles, we're going to say that 1.76 moles over liter is going to be equal to X over 0.572. And so our moles of HCl will be equal to 1.00672. Okay. But that gives us moles of HCl. What do we need to use, or what moles we need to be in order to solve this question?
Hydrogen sulfide.
Yep, right. We need to have our gaseous product as our moles. So how are we going to get from moles of HCl to moles of H2S? And so, right, we can just use our coefficients in front of our two compounds here, excuse me, in order to find how many moles we would have. So what's our ratio between HCl to H2S? 2 to 1, right? So we can say that we can have 1 mole of H2S to 2 moles of HCl. And so we get half of our product, but 0.50336 moles of H2S. What questions do we have so far on having to do this? Does that make sense so far? Yes. Okay. All right, so now we have moles of HCS. So now we're looking for our volume. So what equation are we going to use from our gas laws? We're going to use our ideal gas law, or PV is equal to nRT. What are we solving for here?
Volume.
We're solving for volume, so we know that volume is going to be equal to nRT over P. What do we need to change, or do we need to change anything from the values given?
The milliliters into liters.
We already did that.
Oh.
So what else? In terms of like our gas laws.
Change the temperature to Kelvin.
We need temperature to Kelvin, and anything else?
Pressure to atmosphere.
Good, we need pressure to atmosphere. So we know that our temperature is going to be 22 plus 273. Five Kelvin. And then does anyone know the conversion factor from torus to atmosphere?
It's divided by 760.
Yeah, awesome. Right, so 1 ATM is equal to 764. We can take 1,334 divided by 760. That's 1.75 ATM. Is there anything else we don't know? Nope, looks good to me. So now we can take our moles. We have 0.50336 moles. What value of R are we using?
0.081.
Yep. And then we have temperature equal to, we said 295. And we can divide by our 1.75. Okay, and this is in meters. I believe the question was asking for it in meters, so. We could put this.
Essentially for this one, it's, you're just finding, what is it, the moles, what is it, the hydrogen sulfide originally.
Yep.
And then just plugging that into the ideal gas.
Yep.
Okay.
Yeah, so you're just basically using, it's like a limiting reactant question, right?
Mhm.
Right, if you were given, since both of these are aqueous, you could be given a concentration and a volume for your sodium sulfide and your HCl and ask like what the volume would be. And so then you could just do your normal limiting reactant type of question, find out how many moles of your H2S would be produced. And then once you get that mole, use your stoichiometry in your gas laws question.
Okay.
Yes.
How do we know the first one was the, like, it was abundance, and like, how do we know that one was the limiter?
It told you the question was going to be abundant, yeah. If they gave you a concentration and a volume for that first one, then you would have to do the limiting reactant question, but it said it was an excess in the question. Yep, good question. Anything else on this one? This just kind of pulls in that flow chart she showed you, I think at the end of chapter 5, where you're getting like a gram and you can get all the way to the liters of it or something like that. So that's what she's looking for there. Anything else? Alrighty. We'll talk about your valence electron question. Is there a specific one that you were looking at, or you just kind of know the concept?
It was, I think it was the whole gas notation of copper.
Okay,
It was like 4s1 3d10 rather than 4s2 3d10.
okay, awesome. So, great question. So when we look at valence electrons, we can consider our valence electrons everything outside of that noble gas notation that we talk about. So let me. So we look at the periodic table, right? Our noble gases are going to be in purple here. So if we're looking at argon and like anything in this fourth period here, all of these would be valence electrons, because argon was the most recent noble gas that we looked at. Okay, so let's look at copper, right? What would be the, right, if we were to fill in its electron configuration, what would be the notation for that? How would we write that?
The whole thing.
I guess like using the noble gases.
Okay. Well, I thought it was gonna be for argon 4s2 3d9.
Okay, awesome.
Is that things that she was talking today about, like there being a transition metal exception?
Kind of. Okay. So if you're looking at the periodic table, she was kind of talking about this in class today too, in terms of like your P block, your D block, and all that fun stuff. So we always know that these 2 rows are going to be your P block. These 6 rows over here, or these 6 columns are going to be your P block. And this right here is kind of obvious as the D block in the color form. And then down here you have your F block. Okay, so as you're filling across, you can always say, okay, this is right, this is all your N down here. So this is N, 1S, 1S2, and then this is your 2S, your 2P, your 3S, your 3P, right? That makes sense. 2 and 6 for all of those. 4S, but then we get to 3D. We know that, like, right, once we get to N is equal to 3, we have 3 options. So we need to make sure that we fill in the 3D first before we go down to the 4D. So your D block will always be 1 behind whatever energy level it's in. This is 3D, 4P, 5S, and then 4D, and then 5P. 6N, we jump down to 4D or 4F, excuse me, in your bottom row, because right, you have to fill the 4F before you can fill the 6F. And then we jump back up to your 5D. So your D block will always be 1 behind, your F block will always be 2 behind. Okay, so as we fill in copper, we go through 4S2 because we get through the P block, and then 3D9. Any questions on how we did that electron configuration? Okay, so now let's look at it in terms of our orbital diagram, right? If we wanted to write out 4S2 and 3D9, I kind of gave it away for the 4S, but how many orbitals does the D orbit block have? It has 5, right? Okay. How many electrons go in your 4S? 2. Okay, and how many go in your 3D? And then how many of those are going to be paired? How many of those are going to be unpaired?
4 pairs, just 1.
Good. Right, we're going to fill them up, all up arrows first, and then go back for the down arrows. Okay, so when we get to this 4S 3D area, it's actually going to be more energetically favorable for having this 4S at a lower energy to be unpaired, and then fill our entire paired for our D. So this down electron here is actually going to bump up to this guy here. So now our new orbital diagram is going to be 1 in your 4S, and then pair all of our 3D electrons. Okay, this just makes it more energetically favorable.
Will this always be the case when there's
Yes.
just like one missing?
Yep, so this happens for your copper row or copper column, and then 1 more column. I didn't remember the other column it happens for. I'll pull the trail. So anything in copper's row will be like that. Where else do we think it might happen?
In 17, would that be it? Or no?
It's actually going to happen before copper.
Iron's room.
Very close. Very close.
Very
So so it's gonna be, I'm just gonna tell you, it's gonna be chromium's row. Okay, and we'll talk about why. I couldn't figure out a way to phrase that to get you there. So it's gonna be chromium's row is gonna be the other one,
Okay.
right? For chromium, what's going to be its electron configuration?
4S2, 3.
Perfect, right? So we would say for chromium, we're gonna have argon and then 4S2, 3D4. So if we were to write this orbital diagram, we would say that we have 2 in the 4s. And then how many in the D? 4. Are any of them going to be paired? Nope. Okay, so you have 4 electrons unpaired. So now it's going to be more energetically favorable to have this unpaired electron hop up, or this paired electron hop up to be unpaired. Again, the downspin arrow hops up to here. And so then it looks like we have 5 unpaired electrons in the 3D and 1 unpaired electron in the 4s. Okay, electrons don't have to be paired if they don't have to be. They are the same charge, even if they are upspin or downspin, so they are having a little bit of repulsion. So having them all unpaired means that they don't have to compete with space for any of the other electrons. So this just makes the energy more energetically, or the atom more energetically favorable, right? If you think about it, you would rather be laying down than standing up at all times. So here the atom is laying down instead of like sitting upright.
So for electrons, pretty much it's just trying to fill up all the boxes.
Yeah. Yep.
So everything in chromium's like column will look exactly like that.
Yep.
Okay.
So, right, it'll just be 1 behind. So one will be 5s and then 4D or something like that.
And do you write it in that order, 4s and then 3D, or would you write 3D and then 4s?
I tend to write them in the way that they're filled.
Okay.
So like lower energy on the left, higher energy on the right.
So having like 3D and then 4s.
So having 4s and then 3D.
Because like whenever you're clicking off the stuff, you
Mhm.
take 4s off first, right?
Yes, yep. So as you're like filling it, you want to go from lowest energy to highest energy. So that's 4s to 3D. And then, but when you're taking off valence electrons, you want to go from the highest N value.
Okay.
So that would be 4s.
Why does 3D have a higher energy though? Sorry, I keep cutting you off.
So, I don't know why it has a higher energy level. I believe it's just like in terms of like orbitals and distance away. It's probably some mathematical equation that I don't go into.
Oh, yeah.
But based off of the periodic table, how I was showing you where it's like the 3p and then 4s and then 3d, they go in order of increasing energy that way. So you always know that 4s will come before 3d.
Okay.
And that's the thing with like the diagonal line she was showing you in
Okay.
class too.
Okay.
Yeah. Yes.
And then kind of going along with that, would 4P come after 3D?
Yes, yep.
Right.
So, right, 4s and then 3d, and then the next thing is gonna be 4p. Your P block and your S block will always match whatever row it's in.
And then the 4P would just be 6.
Yep, it would just be 6. So if we were to continue, right, if we wanted to do bromine for this. We would say that this was AR 4s2, 3d10, 4p5. So if we write out, it would be 4s, 3d, and then 4p.
Are those the only ones that have exceptions? Everything else will be true.
Yep, everything else is the same. Yeah, so the only exceptions you need to know are chromium and copper. Okay, so then if we were talking about like ionization energy today, right? We're talking about bromine. We fill in the electrons for this one. If we're talking about ionization energy, can anyone remind me what ionization energy is?
The energy it takes to combine?
Nope. You're very close. You're thinking of electron affinity from cation to anion.
I just remember that like if you go higher up in the periodic table, that gets higher.
Yep, so we're going from like anion to cation almost. So your ionization energy is the ability to remove an electron. Okay. Right, you're making it an ion. In this case, the ion is going to be more positive. You're not making an anion, you're making it a cation. So if we're talking about ionization energy for bromine, we're removing electrons. We're going to remove a 4p electron first. and then another 4p electron, and then another 4p electron, and another 4p electron, right? We're gonna move 5 4p electrons first, and then we're gonna go to 4s or 3d to get rid of the 6th one.
Oh,
Right, if we get rid of all these, all 5 of these, are we gonna remove the 6th ionization energy from 4s or 3d? 4s, right? This is still the higher end value, so we're gonna get rid of these 2 electrons before the 3d. Right, that's why we say that there's 7 valence electrons for bromine when we talk about like Lewis structures. Because it's only missing out of its highest energy level, is only missing 1 of those electrons.
How is that different than electron affinity?
So electron affinity would be if we wanted to put an electron here, right? What would it take to put this blue electron in here? So ionization energy is the ability to remove an electron. Electron affinity is the ability to put an electron on. Okay, so what's going to be easier to do? Remove an electron from bromine or put an electron on bromine? Put one on, right? It's very much easy. It's very easy to put 1 electron to make it look like a noble gas, right? This electron affinity is screaming to be the next, or this electron configuration is screaming to be the next noble gas we have. So it's much easier to get rid of these, or much easier to just make this a 6 rather than to get rid of the other stuff in there. Okay, so that's why bromine likes to become a anion with 1 electron, because it's very close to that next noble gas. Where on the other hand, like potassium or sodium, right, they're 1 away from the gases. Doesn't all make sense now?
Yeah, a lot more.
Tell me, chemistry can cool. Okay, what other questions do we have?
I have one on the homework for tonight, or just kind of went over it a little bit in class today. It was the like graph stuff, where we talked about ionization energy.
Okay.
Like that.
So continuing with that, right? If we look at, I'll just pull below. Let's do, we're going to do period 3, right? So we're going to look at sodium and magnesium, and that row over there. I'll write it again so that we know which one it is. I do know the periodic table song up until iron, so. Okay, so here are these, this is period 3. Okay. So when we look at like the electron configuration for all of these, right, we would have 3s1, this would be 3s2. I'm just gonna write out the like highest one, 3p1, 3p2. Okay. Right, when we look at sodium and its orbital diagram, is it going to be easy or hard to remove that 1 electron? It's going to be pretty easy, right? This is going to be easy because there's only 1 in there, it's unpaired. Even though it's close to the nucleus, right, there's a lot of shielding going on because it has that first energy level and that second energy level that's happening, so it's a little bit farther away. And so this one is going to be, if we put it on a graph, right, this might be sodium here. Okay. What about magnesium? Is it going to be easier or harder to remove that one, to remove 1 electron from magnesium?
Easier.
Right, if we had magnesium, how many electrons are in magnesium? 2. Is it going to be easier or harder to remove 1 electron? It's going to be harder, right? It's going to be harder because now these are paired, right? Those are creating a little bit more energy. And so it's going to be a little bit more difficult to plug in and pick the one that you want. right? If two dogs are fighting, right, it's gonna be hard to get one of them out because they're both kind of gonna be entangled, right? So it's gonna be a little bit harder, but still fairly easy. So we're gonna say this is magnesium. Okay, but now we move, yeah, sorry, go ahead.
So that's pulling like the first electron out, but if you're pulling the second one, would it be even with sodium?
That's a really good question. So if we were looking at, right, this is first ionization energy. Right, so if we're talking about the second ionization energy of magnesium, right, to make this magnesium 2+, what we have to look at, and this kind of has to do with atomic size that we were talking about today. How many protons does magnesium have here? It has 12, right? So when it's just magnesium, we have 12 protons, and how many electrons do we have? When it's just magnesium, 12. Yep. Okay, so our proton to electron here is 1 to 1, right? Each person has one dog that it's holding on to. Okay, each one has a button. When we talk about magnesium plus, how many protons does it have?
13.
It's 12.
It has 12 protons still. How many electrons? 11, right? We lost one electron when we removed it here, right? That's what we said was our ionization energy. So now our buddy system is a little skewed, right? We have more protons than electrons. So that's like saying that these 11 people all have one dog, but now there's one person kind of helping out with all of them, right? So now it's a little bit easier to hold on to them, and you can keep them closer, right? You kind of think of this also as like summer daycare, right? If there's one counselor for every kid, they're going to stay a little bit closer. But now if you have more counselors than kids, they're going to stay even closer. They're not going to get farther away. Whereas if you had more kids than counselors, right? Someone might be over in left field and, run away. Okay, so now you have a better buddy system. Now, if we're going to try and remove it to make magnesium 2+, how many protons do we have? We had 12. How many electrons do we have? 10, right? So now that we have this buddy system, does this radius get larger or smaller in comparison to magnesium? Smaller, right? So it's a little bit closer. It's when it gets closer to the nucleus, does that make it harder or easier to remove the electron? It makes it harder, right? So if we have 12 and 11 electrons, do you think this sodium ionization energy is going to be less or more than this magnesium energy? More. It'd be more, right? So even though they have the same number of electrons here, right? Sodium has 11 electrons, magnesium has 11 electrons. Since it's now closer to the nucleus, it's going to be harder to remove. So your second ionization energy is actually going to be more than your first ionization energy for magnesium plus. So if you're looking at just magnesium, it would be like ionization energy 1 is going to be 10. Magnesium plus, so your second ionization energy would be like 20. Right, so this one's only going to take 10 energies, this one's going to take 20 energies. Okay. That's because we have more protons and electrons, so it's getting closer to the nucleus, making it harder to remove.
So in comparison, what would like sodium's energy be?
So sodium would be here, magnesium would be here, magnesium plus would probably be up here.
Oh. So, so it
Right.
doesn't get easier.
It
gets
doesn't get
harder.
easier, it gets harder, yep. So if you're looking at sodium ionization energy, this might be like 5.
Do you think it'd get easier if there's like only one on?
Right, because there's less electrons,
Yeah.
but when there's less electrons, they get closer to the nucleus. And so it's kind of like a kid with candy, right? He wants all of his stuff to stay still there. Does that make sense why that happens?
Yeah.
I'm gonna remove this guy so we can still talk about the chart. Okay, so now when we look at aluminum still going across the period, how many electrons do we have in the P subzone? We only have 1, right? So do you think it's going to be easier or harder to remove that 1 electron? gonna be a little bit easier, right? So if this is 5, this is 10, aluminum might be like 8, right? Gonna be a little bit higher than sodium because it is in that higher energy level. But it's gonna be a little bit less hard than magnesium because it's only that one unpaired electron. So we might sit down here for aluminum. Okay, what about silicon? Is that gonna be more than magnesium or less than magnesium? Or yes, I'm sorry, more than aluminum or less than aluminum? More than aluminum, right? We now have 2 unpaired electrons in our p orbital, so those are kind of competing with each other. So it's probably gonna be more than magnesium as well, so it's probably gonna be around here.
And why is that higher than magnesium?
Because it's just in the, like, your p is in a higher energy than your s,
Okay,
so it's a little bit farther away from the nucleus, make it just a little bit easier.
but aluminum is smaller than magnesium.
Yes, yeah. So that's our first dip we see.
Wait, why is aluminum smaller than magnesium?
Because it's only one unpaired electron.
Oh,
So it's still going to
Okay.
be higher than sodium because it's a little bit farther away from the nucleus, but your magnesium is still going to be higher because you have to get rid of that unpaired stuff here.
thank you.
Okay, and then what about phosphorus? Do you think it's going to be more or less than silicon? More. Yep. Yeah. Okay, then what about sulfur? What do you think about sulfur? Do you remember what she talked about in class today? What would sulfur's orbital diagram look like?
2 unpaired, 1 paired.
Good. Right, so we have 2 paired and then 2 unpaired. So do you think it's going to be harder or easier to get rid of that one paired electron? It's going to be a little bit easier. Your sulfur is going to be pretty good about giving this one up. So it's probably going to be in between this silicon and this phosphorus. So you're going to dip down a little bit more for your sulfur.
Do they give up the paired one or the unpaired?
It would give up the paired one.
Okay.
Right, it's gonna, your electrons want to be unpaired if possible. So if something's paired, it's gonna be like, please leave. Okay. And then we're gonna go higher or lower for chlorine. We're gonna go higher. And then how would we think it would remove an electron from argon? Super hard, right? That's gonna be the all the way. Right, so it's gonna go this dip, go up, dip, and then super high, right? Argon almost never gives up an electron. So it's gonna be really hard to remove that. It already has its full octet. There's 8 electrons there. It's very, very happy. It does not want to be disturbed. Right, it is laying down asleep, like in its REM. It is ready to go. So it's gonna be very hard to remove an electron from the outside of argon. Okay, does that help a little bit with the stepwise of that question? So it'll always happen that way too, right? You're always gonna dip down in that 3 row and then, or 3 column, and then the 7 column. 3, 4, 5, the 6 columns. Okay, so it's always gonna be like boron, aluminum, gallium, they'll all look the same, and then oxygen, sulfur, selenium, those will all look the same as well. What other questions do we have?
So those are the 2 rows where there would be like dips because it wants to give it away.
Yep, it's easier to give away. Right, so we talked about weird electron configurations. So it's going to be chromium and copper, and then weird ionization energies is going to be boron and oxygen.
There was another class where it had like potassium, gallium, and calcium. And then we had to talk about the number of electrons removed, and it had it like straight here.
Yeah.
So it had it like, there was like a break here and it changed to explain like that break, is that just the ionization
Yep.
level?
Yep, so that's just the ionization level as well. So sometimes I know when I was taking this class, I saw a couple of ionization energy question facts like this. So they asked you like based off of the ionization, so if they said like this is an atom's ionization energies, they would give you the first ionization energy, the second, the third, the fourth, and then the fifth. Maybe it's 10. 100, 1,000, 6,000. Hey, and then they would ask you, what atom is this? From the second period. Hey, how would you think you would go about solving this question? What are you looking for?
The P where there's 5 electrons filling it up, and then there's like one missing one. Like that would be the element, because it was like really hard to give away. Wait, no, no.
I like your thought. Maybe you should just tweak it a little bit. So when does it become extremely hard to remove an electron from an atom? When what is filled? When the orbital is filled, it gets really hard, right? It gets really hard when that is like an octet, or in this case, if it was like the second the s orbital that was filled, right? So we're looking here, we're saying, okay, big jump, not crazy, right? To go from 10 to 400's a big jump, but to go from 400 to 5,000 is a really big jump, right? So you're looking for the biggest jump in your ionization energy. So between the second ionization and the third ionization energy, this is your biggest jump, or your largest difference. Right, so we're saying that, okay, from the second ionization energy, that gets us to an octet, or that gets us to a noble gas. And now we're removing an electron from what looks like a noble gas configuration. Okay, so how many electrons did we remove before we got to the noble gas configuration? We removed 2, right? So if we removed 2 electrons and then looked like a noble gas, and we're in the second period, what atom are we looking at? We removed 2 electrons and then got to a noble gas. Which one are we looking at from the second period?
The noble gas in the second period, or is we in the second period and the noble gas? Like,
We are in the second period, and the noble gas would be in the what period? The first period, right? So yeah, we're going to be beryllium, right? Because we removed 2, and now we're removing from that from helium. Okay, does that make sense? So that's what that graph is showing you,
Okay.
just as a graph rather than numbers.
Okay,
Okay,
so wherever the biggest jump is, no matter what, that's where you're reaching the double gas.
yep. Yep.
Thank you.
Right, so you're gonna have a really hard jump when you're removing, right, like bromine, we were talking about that earlier, like, right, this is always going to increase as you remove these electrons.
Yeah.
And it's going to be pretty hard over in this, like when it looks like calcium and potassium, but it's going to be the hardest once it looks like argon. Okay, yes.
on your little diagram though, the energy was still more than that big jump.
Mhm.
Like, because I thought the jump to take the first one off the noble gas was supposed to be the hardest.
Yes, so right, once we got to here, this was our hardest jump, right? So once we removed the 2, right, like, the first one was easy to get rid of, second one a little bit harder because, right, we now have more protons and electrons.
Yeah.
But now that we're trying to remove this ionization energy, right, we're moving from a noble gas, that is going to be the hardest. And we require this much energy to remove that electron.
But isn't like the next one harder? If it's,
Yes, that's harder, but we've already made that big jump, right? It requires more because we're still trying to get rid of those electrons. But this is not the biggest jump we have because we've already reached the noble gas.
so it's more about the jump. not
It's
the-
more about the jump and not
And
the
not the
actual value.
actual,
Yep.
So the sixth or the fourth, you would already be like an argon or.
Yeah, you would already be a noble gas.
Okay.
Yep. You would be removing, right, here you're removing the 8th electron from that noble gas.
Yeah.
Here you're removing the 7th electron from that noble gas. Or the
Oh, okay.
6th electron.
Oh, okay, so then like you would, by the time you get to the big ionization, you would be like 2 more over.
Yep, yep, so if we said this was the 3rd period instead. Then we could say. Right, we're magnesium, so now we're removing at that 3rd ionization energy, we're removing the 1st electron from argon. Then removing this, the electron from chlorine and the electron from sulfur, like that kind of what it would look like there. Right, so you're taking more of that noble gas configuration and pushing it closer, so you're just increasing the number of protons you have in comparison to your electrons.
Okay.
so wherever the biggest jump is, that's where we hit the noble gas.
Yep, that's what it, when it looks like a noble gas,
Oh,
Yep. when it's isoelectronic with a noble gas. Yep. How do we feel? Better?
Yes.
Okay, awesome. I think I don't have a review session next week, because it's spring break. And then I believe your exam is the week after, right? We have 1 week and then the week after. I believe that is a Wednesday. It's a Monday? Okay, whenever it is, I'll make sure I hold a review session on Zoom again before that, so I'll have that Wednesday when we get back from spring break, and then I'll do an extra Zoom review before that one.
okay.
But in the mean,
It's like right before we come back from spring break. Angela said we did, but I can't remember.
like,
Oh, no.
Yeah,
Oh,
like
like
the
the
Sunday
Sunday.
before.
oh, the Sunday before that Monday. If you don't have one this week, you might. If that's the case, I'll put some like practice problems for you to do.
Forget everything.
Yeah,
No, forget about that.
That 1 week is gonna like reset.
yeah, I'll try and do, did anyone look at my notes that I posted this past week?
Yeah.
Was that a little bit helpful with like a
Yeah.
little bit of the notes
Yeah.
and then practice questions? Okay,
Yeah.
I'll do that again. For this next one, especially if there's like a spring break in between.
Yeah.
And I'll try and continue to do that moving forward as well.
Wait,
Alrighty.
where are you posting those notes?
So I usually make an announcement for it and then I'll always post it in the office hours section.
Oh,
So I'm just like adding to all of my stuff. It says like review from this day, review from this day. But I try to put an announcement out as well.
Thank you.
Of course.
Thank you.
Thank you so much. I'll post this as well. I think my Zoom went okay. So we'll see how that worked. Thank you for coming.
So the resources that are on the quizzes, will they be on the exam as well, like the equations and stuff?
Yes, yeah,
Okay.
yeah. If you get them for a quiz, you should expect them for an exam as well, I would say.
oh,
Yep.
So just to reiterate, so if you have the greater number of what is it, I forgot what they're called, the NM wavelength,
Yes,
so then that's what you can't see.
right. Yep.
Okay.
Yeah, so you can see anything below that because your smaller wavelengths
Yes.
are more, thank you, are more towards like the red spectrum. And so we can see red more
Yeah.
easily than we can see like violet.
Oh, okay. Yeah, because what is it on this past quiz? That question, and I forgot which other one. Like, I'm pretty sure I got those wrong.
Okay,
I'm pretty sure.
I know that those